Today we are going to talk about circular motion. This is equally important as motion of a particle in a straight line or a plane. Now if we can remember, while studying the motion of a particle in a straight line or in a plane, we have used the Cartesian coordinate system. We describe the position of a particle in terms of x and y. To describe the motion of a particle in a circular path, we use a different coordinate system called the plane polar coordinate system. Now, what is this? Plane polar coordinates makes it very simpler or very easier to describe the motion of a particle along a circular path instead of the Cartesian coordinates. Now, what are the coordinates? What are the variables that we need in plane polar coordinates? We need two variables. Here, this is the center of the circle O, and we draw axis OX along x-axis and OY along y-axis. Suppose at any instant of time the particle is at P, which makes an angle theta, and the radius of the circular path is r. So these two just we need. So the angular variable to describe the motion in a circular path are r and theta. Just as we needed x and y in Cartesian coordinate, we need r and theta in plane polar coordinates. So r is here the radius of the circular path, theta is called the angular position here. Now suppose we know that the particle is at P at time t. Now the particle moves towards P prime at time delta t and makes an increase of angle delta theta. Now what is the rate of change of angular position with respect to time? It is nothing but delta theta by delta t. If we take the limit delta t tends to 0, this term is d theta by dt. It is called the angular velocity of the particle and is represented by a Greek symbol called omega. So this is angular velocity. If we differentiate this omega again with respect to t, we get the angular acceleration, which is represented by another Greek symbol alpha, d omega dt. In terms of theta, it is a second derivative of theta, d theta, 2 theta by dt2. This is called the angular acceleration. So far it is clear? Okay. Now, from the motion of a particle in a straight line, we used to have those three equations, if we can remember, for a constant acceleration. What are those? Those were s equals to ut plus half at square. Second one was v equals to u plus at. Third one, v square equals to u square plus 2as. V is the final velocity, u is the initial velocity, a is the acceleration which is constant, t is the time, s is the distance traveled. Similarly, we can get or we can write three equations with respect to the variables we got here. So what were the variables? We got r, theta, omega, alpha. Omega is nothing but d theta by dt, alpha is nothing but d omega by dt. So s, the analogous of s in plane polar coordinate is theta, and v, the analogous of v is omega, analogous of A is alpha here, so we could write that theta equals to omega naught, which is the angular velocity at t equals to 0, and half alpha t square. Second equation is omega equals to omega naught plus alpha t. Third equation is equals to omega square equals to omega naught plus 2 alpha theta. I hope it is clear. Moving on. Now the particle moves along the circular path. The distance is traveled at time delta t is p to p prime. Now this is not a straight line, it is on an arc. So for a very less value of theta, the distance the particle traveled is delta s equals to r delta theta for very small value of delta theta. Dividing with respect to time, we could get the linear speed of the particle. We cannot talk about here the velocity of the particle because the direction is always changing as the particle moves. I will show in a moment how the direction changes. Now at limit delta t tends to 0, this becomes the velocity, the speed of the particle, which is ds dt. It is nothing but r d theta dt or r omega. Differentiating with respect to time once more, we get the acceleration. We write it as a with the suffix t. I'll explain why. Is nothing but dv dt equals to d2s dt2, or in terms of angular variables d omega dt or r alpha. The t suffix here represents that, I'll explain shortly, that this acceleration is actually the tangential part of the net acceleration. It is not the net acceleration, it is the tangential part of the acceleration. So what are the findings we got from here is that v equals to r omega we can write, and we could write that at equals to r alpha. Okay, so far it is clear. Now, just as in Cartesian coordinate system, we have the unit vectors along x-axis is I cap, unit vectors along y-axis is j cap, we can remember, and the position vector we used to write like r equals to I cap x if this makes x and if this is y. We could write I cap x plus j cap y. The position vector is written here in Cartesian coordinate system. We have to write the position vector in terms of plane polar coordinate system. So what could be this? So the position of the particle at time t equals to at p. So r can be written as the value of r and the unit vector. So now I have to define the unit vector here. So what are the unit vector? As we can remember, we always define unit vectors along a variable in the increasing direction of the variable. So what are the variables in the plane polar coordinates? One is r and one is theta. We get the unit vector in the increasing direction of r, and is suppose it is towards a point A, and we represent the unit vector in the increasing direction of r by er cap, and we get the unit vector in the increasing direction of theta, and towards the point B is e t cap. T is represented here because of it is along the tangential at the point P. Now we have to write this ER and ET in terms of the Cartesian coordinate system to make it simpler. So how we can write this? We could draw a parallel axis at point P, Px prime parallel to x-axis and Py prime parallel to y-axis. Now how we can write this ER and ET in terms of Cartesian coordinate system? I'll show. So ER is making a same angle as this R makes an angle with x-axis. So ER equals to this PA I cap PA cos theta plus J cap PA sin theta. Now the value of PA is 1 as this is a unit vector. So I cos theta plus J sin theta. Similarly, we can write the ET equals to I PB pi by 2 plus theta I cap PB cos pi by 2 plus theta plus J cap PB again sin pi by 2 plus theta. Clear so far? So in the second coordinate, in the second quadrant, the cos is negative, so we get, and the value of PB is 1, so we get I minus sin theta. In the second quadrant, sin is positive, so we get PB, as PB goes to 1, we get the cos theta. So it is nothing but minus I cap sin theta and J cap cos theta. These are the two very important relation between the unit vectors among two different coordinate system. We'll write down here ER equals to I cap cos theta plus J cap sin theta. ET cap equals to I cap minus I cap sin theta plus J cap cos theta. Okay. I hope so far it is clear. Now we have not defined any direction to the velocity and the acceleration. Now what is the velocity here? First let's write the position vector of the particle in terms of the plane polar coordinates. Suppose this is R. R is nothing but the value of the position vector and its direction, which is radially outward. So this ER is called the radial unit vector and ET is called the tangential vector. So R is nothing but I cap cos theta plus J cap sin theta. If we differentiate R with respect to time, we get the linear velocity. So linear velocity is nothing but dr by dt. R is constant here. We have to differentiate this term with respect to time. And this is a variable of theta, so we will get an additional d theta by dt term. So this is minus sin theta d theta by dt plus j cap cos theta d theta by dt. We know that d theta by dt is equals to the angular velocity and can be taken out as it is present in the both term. In the bracket we remain with I cap sin theta and j cap cos theta, which is nothing but the tangential unit vector. So et cap r omega et cap. So this r omega is the velocity, is the value of the speed, and et represents the direction of the velocity. So at any given instant of time, wherever the particle is, the direction of the velocity is always towards the tangent. If the particle is here, it is along the tangent. If the particle is here, it is along the tangent. Now how we can calculate the acceleration? We again differentiate with respect to time. So A is equals to derivative of the linear velocity is equals to, we have to take the time derivative of this term. So here omega and this term are both variables. R is a constant, so R can be taken out, and d theta dt omega, inside we have minus I sin theta plus j cos theta. This is nothing but the differentiation of two product variables R. First we keep omega equals to constant and take the derivative of this minus I cos theta d theta by dt plus j minus sin theta d theta by dt plus this term is constant, we keep this as is, and we write this d omega dt Got it? So this d theta by dt again equals to omega, can be taken out. So omega will be omega square, and minus in the both term it can be taken out. So inside will be minus omega square, and we are left with minus I cos theta plus j sin theta, and this term, which is this, is minus I sin theta plus j cos theta d omega dt here. So a is nothing but minus omega square r, and this term is nothing but e r cap, and if we take r inside the derivative, we get this is, we get dr omega by dt. This is et cap from here. So if I write omega equals to v by r into r and square er cap, this is nothing but v, the linear speed of the particle, and it is et. So this is minus v square by r er cap and dv dt et. We have seen that the linear velocity of a particle in a circular motion has only one unit vector, but in acceleration there are two unit vector present. One is er cap, one is et cap. Now if we can remember that in this initially we have described this term at. This is nothing but the tangential component of the acceleration.